All right, so today is lecture 11c for the SVM optimization and the dual formulation. So I'm going to introduce just the basics about how do you derive the dual of SVM objective formulation. So before I go on, I want to summarize. So in SVM, we covered the margin definition, the basic optimization for the linearly separable case. And then during last class, we covered non-linearly separable case. So non-linearly, in the end, we use a kernel trick to extend x to phi x. But in the SVM case, we don't directly write out phi x. We write out something called kernel, which is equivalent to phi x transposition phi z. However, we don't really need to know about what is phi x and phi z. The reason behind this trick is, so first it's for computational efficiency, and there's also reasons later is to control the number of parameters. But the controlling of the number of parameters is related to both the kernel representation and also the dual form of the SVM, the optimization. So today I'm going to focus majorly on linearly non-separable case, which you can call that a soft SVM. So what we covered, you can see, name it as a hard SVM because we assume the data can be completely separated, nicely separated into two classes completely without making the error. So because in our formulation, we require every sample to be predicted correctly. If you remember our old objective function. So today I'm going to relax it to allow some errors to exist. Okay, so today we're going to focus on the revision of the scoring function. And in fact, this is a new loss function we never introduced before, which is called hinge loss. Okay, so let's recap what we learned before about linearly separable SVM. So we try to achieve two goals. First goal is to minimize the margin. It's equivalent to maximize the W transpose W. And at the same time, we want to correctly classify all the points because we assume this in the hard SVM case, we can't. There actually is solutions. There are solutions can correctly classify all the training points. So the formulation we had, I already emphasized many times, but just to recap, to hopefully you're going to easily connect it to the next non-linearly separable case. So in the linearly separable case, we minimize W transpose W over 2. At the same time, for those points from the positive class, we want the W transpose Xi plus B larger or equivalent to 1. And for those points in the negative class, we want their W transpose Xi plus B smaller or equivalent to -1. And then that makes the multiplication of the label, the true label, and this function to be always larger or equivalent to 1. So this function actually is a summarized way to guarantee all the training samples are predicted correctly. And I'm looking for the W and B that can make sure all the training samples are predicted correctly, using this as a constraint in my optimization. So this is the summary, and we already learned about this many times before. All right, so now let's look at this case. However, so for example, the two classes are very nicely can be the majority of the points can be nicely separated, but they are noisy samples. So in this case, these two blue samples are in the dense red class size, and these two red points are on the dense blue class size. So how do you represent this? So I still want to minimize the maximize the margin, which equivalent to minimize W transpose XW over 2. But now I'm not looking for classify all the points correctly. My goal changes to, my constraint changes to, I want to minimize the number of classification errors I'm making in my training data. So now I still have two goals, but a slightly different goals compared to the to the separable case. I want to minimize W transpose W over 2, at the same time minimize the number of errors I'm making on my training data. So in fact, this number of errors, this formulation, it's extremely difficult to optimize. It's not differentiable, and it's just very hard to formulate it into a differentiable function. So that's why, that's actually next page. So for now, I have two goals. The easy way to combine the two goals is I want to minimize this W transpose W over 2 plus minimize the number of errors. So I'm using a parameter called C, a hyperparameter, shows the trade-off between the number of errors I'm allowing versus the trade-off, the margin I'm trying to maximize. So margin, maximize the margin, at the same time minimize the number of errors. So if you can connect with the ridge regression, we had in the ridge regression some formulation actually like this, right? So we have lambda, we use beta, but its theta is the same. Lambda theta transpose theta plus the MSE loss, actually these SSE loss, sum of squared error loss in the ridge regression. Our lambda at that time is before the O2 penalty. And this time, if you do a one-to-one kind of analogy, looking at the ridge regression versus SVM, you can tell, and SVM performs some type of L2 regularized loss formulation too. Just differently, this time we don't put lambda before the regularization, we actually put that weighting term C before the number of errors we are making. And of course, they have this reverse type of proportional relationships, right? The larger the C, the more penalization I'm penalizing on the errors, which means I don't want to make errors. If I have an extremely big C, I want to minimize the number of errors, my searched WB, as much as I can. So so they're the same formulation, but just this time I put the weighting hyperparameter at before the error term. And this is exactly that hyperparameter you're going to tune using cross-validation in the homework. And that's actually for SVM, the most important hyperparameter to tune is the C parameter. All right, so like already mentioned, the number of errors, that type of count-based error representation or loss formulation is extremely difficult to optimize. So people looking for the similar loss formulation, but you can easily perform differentiation on top. So the simple one of the simple one is actually this loss. It's called in fact, this is hinge loss. But for now, just this, I'm trying to, instead of minimizing the number of errors, the number of training points that are predicted wrongly, I'm minimizing the wrong distance. So if you're predicted correctly, you're not going to count that distance at all. However, if this point is not predicted correctly, it's on the other side of the correct margin, correct boundary, you're going to use that epsilon as part of the loss formulation. So for each training point, you're going to have a epsilon I parameter to look for. So for example, this red point, that this is epsilon j, the number of error it's contributing is this distance from the point to this +1 point, because it's supposed to be on the left side of the red point, but it's on the right side. So that's why you're using this distance to show how much error I'm making on this point. For each data, you're going to have epsilon I to show the distance of that point to the correct boundary, to the correct plane. So it's the correct plane. If it's already on the correct side, the contribution will be 0. So that's guaranteed through this formulation. If the point is positive class, I want to guarantee WXXI times W transpose XI plus B. This is supposed to be on the positive, that left side, right? Each point's prediction should be larger or equivalent than 1 with a little bit noise. So this epsilon should be always actually larger than 0. So if it's already larger than 1, so if it's already a good, nicely predicted sample, and this equation will be absolutely guaranteed. So I'm trying to see maybe this point, absolutely W transpose XI plus B, because it's on the left side of the +1 plane. And all the points on the left side of the plane will be W transpose X plus B larger than 1, right? That's just guaranteed by the linear function. So this point all the points here will be larger than 1. And of course, it will be larger than 1 minus epsilon, because epsilon is a positive number. Only those points actually on the wrong side, which means, so it's supposed to be larger than 1, but actually it's smaller, it's not larger than 1. So let's see this red point. So this point, I wanted it to be larger than 1, but with a little bit epsilon j noise. So you can tell this point, WX transpose X plus B, larger or equivalent to 1 minus, which is exactly from here to here, which is the prediction of a linear function predicted on that point. And I'm using the epsilon j to represent how much wrong side distance I'm contributing to the noise. Okay, question about this? And then you can do the same thing for the negative points. So this contributes a total of n constraints plus another n constraints to require epsilon I, each epsilon I larger or equivalent to 0. So together, in this soft version, you have 2 n constraints instead of n constraints in this separable hard case. So let's see, this is the separable case representation. And Just two classes can be nicely separated into two, and there's no noise. There's no noise in the middle. But there are points, of course, on the boundary, right? So more correctly, I should draw this blue point here, red point here, because it's the touching the support vectors. The non-separable case, so I'm touching the points, but at the same time, there are noisy samples on the wrong side. And I'm penalizing the wrong side points distance to the correct plane. So now let's see. So why can't I just always assume it's always separable? If you remember, we had this kernel idea. It's the VC dimension, right? We can always project our x into phi x through RBF kernel. In the RBF kernel, it's like infinite number of dimensions. In that type of formulation, you can always, most cases, separate the whatever finite sets of training samples, right? However, so in the end, what we want to balance is we need to consider two. We want to have a large margin, because large margin represent what? Represent generalization bias on the future data. When you have large margin, so in general, it should be performing actually better because it's not modeling noise too much. So then you really need to balance the complexity of the boundary at the same time the margin size. So let's look at this example. So this example only shows you the linear case. So in the linear case, actually, in fact, you can find a margin that without allowing noise at all. So this is the training cases. So this is the train. So the upper is training with a large C. Large C means penalize error a lot. So this is the training case with a small c, which means I'm allowing some errors. So if you look at this, and yes, this completely separate the two cases. However, the margin is relatively small because you penalize loss more. You really leave very little buffer of the size of the margin. You don't allow the margin to be large. So because of this, I mean, in fact, this just of course a little bit speculated, but just trying to give you the concept. For the future data, it's highly likely to going to make errors because of this 3 points. The only difference is actually before from the large C case versus the small case is actually only 1 point. Is to allow these points to be noisily predicted or not. If you allow that points to be wrongly predicted by using a small c, your margin is actually much larger. It have a better generalization, good region or band to separate into classes, and hopefully in the testing data, it can generalize better on the testing data. So in the end, the point is the separable is about, do I make classification errors? And I want to have smaller classification errors, but at the same time, I want to have a good wide band, a wide margin, because this actually is a good bias to hopefully to, not bias, it's actually guaranteed to regularize my model to behave better. You can actually prove it to regularize my model to behave better in the future data. So balance, margin, and number of error I'm making on training data. Okay, questions about this? So this is the train and this is the test. And the only difference is actually is that point. How do you think about that point? But in fact, if you feel, just roughly use your eyes, the negative or the red points are quite nicely densely related to each other in this region, and the triangle points are nicely related to each other in this region, right? It's just use your eyes to eyeball. And this margin actually fit a lot better if you think about the more like this dense regions of each of the class. And I'm trying to use the margin to model as wide as I can the density low regions separating the two classes. All right, so that's about the ideas behind margin and a lot of the soft SVM. So here is more like a summary of large value. Just means classification is bad, but may lead to more expected training error. And a small c result in more training error, but hopefully a better true error. Okay, so what is that epsilon summation formulation? In fact, it's the true loss formulation representation is this. So this is called hinge loss. The formulation is, again, so in the old way I'm writing as summation I from 1 to n epsilon I. Now epsilon I means the distance of, let's actually go back to this page. The distance between the point and the correct plane. But if it's already on the correct side, I do not use that epsilon. So this is very important, which means, so if, let's see what is this loss formulation look like. So this is the +1 plane, -1 plane, red points, triangle points, and then there, sorry, the triangle looks like a circle. So let me try to make it a little bit different from each other. Maybe, yeah, like this, X. Okay, so if I have a circle point here, the epsilon is, this is my epsilon I, right? So, and there's another J points. And the J points actually contribute, it's predicted correctly. Should this point contributing error in this formulation or not? Of course not, right? So this means I can't just directly see it's epsilon sigma I, and those should be the wrong points contributing the distance. And this is totally reflecting this loss formulation. If your yi times the fxi, which is the w transposition x plus b, if it's this, because in the setting, if it's correctly predicted, what should be the number? Larger or equivalent to 1, right? Those are corrected points. If they are correctly predicted, what will be this whole thing? 0. Right, so this is negative, that max 0, and that negative, it contributes 0. But if this is not larger or equivalent to 1, it's actually smaller, what will be 1 minus that part? It will be a positive, that's exactly the wrong predicted point, epsilon I. And by performing max 0 and that distance, you're going to have that epsilon I contributed into that error term. So this is called hinge loss. So this is the right way to write it. So the previous way is just more intuitive way to write the summation of the error. This is called hinge loss. A hinge loss version of the SVM, it's the software SVM we normally see because we allow errors. And the version without allowing error, we call that a hard SVM. All right, question about this? You learned about a good loss for classification, right? Because everything we learned before, sum of squared error, they are the main purpose of sum of squared error are mostly for regression. And this is a very good loss function for classification. Of course, it's based on this type of margin separation ideas. Okay. So now let's look, so we know the loss function now, right? We know the scoring function. So after you know the scoring function, how do you solve it? And this is similar to what we did in the regression case. We know sum of squared error. Then we use gradient descent normal equation just by taking those points, making the gradient equal to 0, and a various of options. So now let's see, how do we solve that margin plus the hinge loss formulation? So this is the summary of the two cases. And to proceed, I have to teach you something about a little bit basics about the constraint optimization. So the optimization review is normally when you think about optimization, you need to consider what is the objective function, what are the variables I'm looking for to optimize the objective function, at the same time, what are the constraints I have to satisfy to, at the same time, and to optimize objective function. So we want to find the values of those variables that minimize or optimize the objective function while at the same time satisfying the constraints. So this is the simplest, a really simple case to show you what do I mean by constraint optimization. So again, whenever you see this objective formulation, 3 elements to clarify, what is my objective function? So in this problem, my objective function is u quadratic. So who is my variable to optimize the objective function, which is u? And what is the constraint? There are only one constraint in this case is I want my u to the final solution u to be larger or equivalent to b, and b is a given scalar. In fact, this solution depends on b. So let's just see, u quadratic function is the simplest function to optimize, right? So if we have only fu equals to u quadratic, what should be the minimal points without a constraint at all? If there's only just minimize fu equal to u quadratic, the best u should be 0. So we normally write the best parameter, the best learned, as a star on the superscript. So the best u is 0, and the best fu star is 0, 2. All right, it's very clear from this kind of bell-shaped function. However, if I require u to be larger or equivalent to b, so what do I mean here? Which means I actually cannot go the right side of b at all. The only choices I can select is from the region larger than b. So this means what? In the first case, I can't even reach 0 at all because b larger than 0. So for the second case, and I can search all the regions that larger or equivalent to b, which is all the regions actually including the global minimal point if without a constraint. So very easy. For the first case, my U star is what? In the first case, who is the best U? That give me the minimal FU, quadratic, U quadratic. Yeah, it's B. For the second case, who is the best U star? 0. This is exactly a simple flavor of constraint optimization. You have to consider constraints. And in fact, it's pretty easy to solve. I'm going to constrain, revise this formulation into something like a Lagrangian form, which minimizes the U quadratic plus lambda. I think I should do B minus U, right? Because it's smaller. I'm going to do the smaller the better. Yeah, it should be B minus U by converting my formulation from a constraint formulation into a Lagrangian multiplier augmented formulation. So who has learned about numerical optimization? Who already took those classes? Raise your hand. Okay, very minimal. Yeah, so there are a lot of contents actually in numerical optimization, cover the properties of function, properties of the constraints, how do you, what cases you can have this formulation, what type of function properties guaranteed to have global optimal. So there are actually it's a huge research field about this. So there's no way we cover, I can only give you just a flavor of the simplest case in this 30 minutes of short introduction. All right, so I show you this, and then 1B, and then we can also tell, I already showed you, the best is, in the first case, the best U is B, and also the best function, best objective value is B quadratic. In the second case, the best is 0, and the best objective function value is also 0. All right, so pay attention to this. In the end, and this is the minimized objective we're looking for, right? We want to look for what is the minimal value for the U quadratic function, which is the FU star, which is B quadratic, is this point. And in this case, it's actually this point. Okay, so now I'm going to move to primal and dual problem. Solving the dual problem, if the dual formulation is easier than the primal problem. So just memorize it. We need to change. So when you want to change the primal problem into the dual problem, you need to change the primal minimization to dual maximization. Or if your primal problem is maximization, your dual problem is going to be changed into minimization. This sounds kind of odd, but hopefully this gives you some kind of intuitive view about this. So I'm changing the primal problem, and my primal problem, the best point, touches the dual problem's best point, and dual problem you need to push up to maximize, and the primal problem actually push down to minimize. And this is almost it's a little bit abusing of the concept, but that's roughly give you the idea. So primal problem actually corresponding, there's a one-to-one mapping to a minimization problem in the dual formulation. It's only valid when the original optimization problem is this problem needs to be convex. If it's minimization, it needs to be concave if it's for maximization. So for those of you who still remember what is convex or concave, so this is pretty intuitive from geometric perspective, but there's a lot of mathematics behind this, and we're going to skip it. So I included a lot into the actual slides, feel free to check those slides out if you're interested to learn more. All right, so let's see, what is it? The primary problem, like I said, there's an objective function, there are constraints. I'm trying to minimize objective function. My variables are W, subject to a series of smaller, this type of inequality constraints. And then I can reconvert it, I can convert the constraint problem into a Lagrangian, generalized Lagrangian form, which is exactly what I did in this. So in the extra slides, I actually proved what is this form's dual formulation, why this formulation's minimal point equivalent to its dual form's maximization. So I can't, because it takes a while for me to derive it, so feel free to check it out. This is a very concrete derivation I did. So minimal of primal equals to maximal of the dual form. Through this really simple example. You can totally prove it very easily. All right, so you have the Lagrangian, and by adding this Lagrangian pliers, which we already learned in the last class, it's just alpha I, and you can also use lambda, whatever, that's just the newly introduced new variables. And then this is your generalized Lagrangian, you can actually prove. So this, you can rewrite your primal form into 2 steps. So this is the summary, because you have not just the W, you also have the alpha to look for, right? Those are also parameters. So this Lagrangian really convert the previous problem with only W into a more parameter with both W and alpha. And now my problem actually has 2 sets of variables to look for. And how do I formulate it? Actually, you can prove it. The good point, the optimal point of that formulation equivalent to you maximize over alpha and then minimize over W. If you remember, if I'm removing this, and this is almost my original optimization, right? Almost. But this form consider both the optimization function, objective function, and the constraint. You have to consider the constraint at the same time. This part include the constraint in the formulation. All right, from there, you just can flip the max and the mean. So you do first the mean over W, then you do max over newly introduced alpha, and this solution, if under strong duality, if there exists a saddle point, so don't worry, in the end, just you're taking gradient of this versus W, the solution, the minimal, the best value of this formulation and best value of this formulation and best value of this formulation equals to each other. This is exactly that. The primal and the dual, the best solution actually is the same solution. And you can prove it under strong duality. All right, question about this? Yeah, okay, I know this is too mathy, but I still want to introduce, to give you a flavor how a lot of machine learning research it's, how people start to derive it and how the important algorithms are designed, how do people design, and what type of techniques people borrow outside the computer science, and this is purely optimization, right? A lot of optimization techniques. All right, so let's use that primal or dual to rewrite the hard SVM. Okay, so this is what we have, objective function and constraints. And then we rewrite it by converting it into Lagrangian form. And this is our W. W and B is our primal variable, and alpha is our newly added Lagrangian multiplier. And this is the thing I showed you last time, and previous few slides explained to you why performing this series of operations. So this is actually the L11c, right? Actually to be more correctly, so this is the dual formulation, because in the primal formulation, I first maximize alpha, then minimize W, and then switch. I got the dual formulation is I first minimize versus the W, and then maximize over the alpha. So how do you minimize over W and B? Very easy. We had it before. Take gradient, set it to 0. And you take gradient, you set it to 0, you're going to derive. So the first thing you're going to get is W equals to summation alpha I yi xi. And the second you're going to get is this. Actually, there's some other constraint you can get it. And then because you can rewrite W just as only related to alpha, you just substitute in the original form using this formulation, and you can do the same thing for B, because this is only for the B. And then you're going to get the dual form has no W and B at all, has only alpha. And this is exactly the left part. Then you maximize over alpha. And this is how we get the dual form. All right. So I know like your most machine learning courses don't cover this, but I really want to cover this. If you just give you a good flavor of why this form, right? All right. So this is our. So let's just recap. Lagrangian multiplier and minimize Lagrangian in terms of W and B, and then substitute W and B with the alpha and yixi. You get the dual form, then you maximize it, and after you have the alpha, you can get W. You can also get B. But in fact, people don't have W and B at all. People just directly performing training by get alpha, then performing testing directly using alpha only too. So, but it's good to understand W is equivalent to alpha I yixi. And this will tells us something in the later slides, give us some kind of intuition about why this is a good formulation, why the dual form is good. Because we said, unless dual formulation is easier, we go to the dual formulation, right? If primal is easier, no need, and not necessary to go to dual formulation at all. Okay, so honestly, I think I already did this, so I don't need to repeat. Original, primal, take gradient, and yeah, this is a little bad. So the previous slide is actually pretty good, and yeah, so don't worry about that slide. So now let's recap. So this is our in the primal space what our hard SVM look like, and this is in the dual space what our SVM look like. So here you have W and B, and you have N constraint. Here you're looking for you look for N different parameters. So here you have W and B parameter to look for. So what's the size of WB? The number of parameter you're looking for is actually OP, right? And the number of parameter in the primal I'm looking for is how many? It's actually ON. So the number of parameter, and here the number of parameter. Okay, so remember that in the primal formulation, we need to look for P plus 1 parameter. In the dual formulation, we need to look for N parameter. Okay. So I don't want to derive, but when you consider areas, the hinge loss, it's extremely easy in the dual formulation. If you remember, in the primal formulation, you had from unconstrained go to 2 unconstrained, the epsilon I, right? I think I had the, yeah, I don't have that. So in the primal, in the primordial space, in the prime space, the margin plus the hinge, just the linear case, the primal linear case, linear soft SVM. So how many parameters do you have? Do we need to estimate? If you just kind of think about, there's epsilon I added in each constraint, right? So how many parameters we need to look for in the soft SVM? You have those epsilon I, right? And you also need to look for W and B. So the number of parameter is O n class P. Of course, you can do class 1, but actually you can cancel it out. But yeah. And in the dual form, in fact, the only differences is you make your alpha I upper bounded by that C parameter, hyperparameter you added. And extremely easy and almost no differences versus the hard SVM case. And there exists very efficient algorithm exists to optimize this. But in the primary case, by allowing errors, you actually got a lot more parameter estimate. And I haven't even talked about the kernel case, right? When you go to the kernel case and when you move to phi x, and the W will be, yeah, so we're going to talk about it later. All right, so, and then also in the dual case, you can perform the test without even have the explicit W at all, because you can just substitute the W through that derivation you get. Sorry, that page is so bad. This W equals to summation alpha I yi xi. You just substitute it to our fx function. The f function equals to x W transpose x. Sine function W transpose x plus b, right? This is our SVM decision function. You just substitute the W equals to summation I from 1 to n alpha I yi xi. And so this is an x test, right? So let me write it as TS here. And just do eyeball, substitute the W to here, you're going to get this. And I'm going to talk later because the majority of the alpha I are 0, which makes the computation here is really only related to those alpha I whose alpha I are not 0 to contribute to the prediction prediction function. So, all right, so this is the hard case, and then this is actually, it's also soft case. Yeah, I should not write. It's actually both. Sorry, don't worry about that. It's for the generic case. This is for linear, just linear case, for linear generic case, soft case. Then during training, we actually had it. So the only thing you require is xi transpose xj, and in fact, what you need is this kernel matrix having xi transpose xj among all the possible training samples versus the other training samples, and you're going to do a summation over
through this evaluation by maximizing this whole objective function, satisfy the constraint, these two different constraints.
Question about this? We talked about it last time, but it's just not very clear what alpha even mean. All right, so we talk about the optimization and how to optimize and using the dual form. And we already had, so there are actual things, but let me, after I finish the next section, I'm going to talk a little bit about the true optimization function people use is because make use of the properties of alpha I. So what is the properties of alpha I? The parameter, those dual parameters. So from the primal to the dual, you actually need to guarantee this formulation. You can derive it. I'm not going to derive this, but feel free to check out my extra slides. So for every I, which means for every training samples, I need to guarantee alpha I times yi W transpose x plus b minus 1 equals to 0. So what does this mean? So this just guaranteed to achieve the optimal point. For all the training points, the alpha I times yi times this prediction function minus 1 needs to equal to 0. So again, let's reconsider our margin view. So this is the +1 boundary. This is the decision boundary. And this is the -1 boundary. So here, W transpose x plus b equals to 1, right? Here, W transpose x plus b equals to -1. The upper larger than 1, lower smaller than 1, -1. Okay, so from this figure, what do you get? W transpose x plus b times the yi minus 1. What's the pattern there? So for the points here, they are W transpose x plus b. Yeah, let me actually write it out. So W transpose xi in the above region plus b will be what? It's just larger than 1, right? If they are larger than 1, because their prediction is 1, their yi equals to 1, right? Their true yi equals to 1, so that's why this prediction is what? This multiplication is guaranteed to larger than 1, and which means this number is guaranteed to be positive. If this is positive, the only way to make this whole thing 0 is what? Alpha I equal to 0. And then same thing for all the points in the very short -1 region, the alpha I, because it's the same thing, right? The yi times xi plus b together -1 will be larger than 1 too. And this region, to make this equation equal to 0, the only choice is alpha I equal to 0. And then that leaves what? It leaves only the points on the boundary inside the margin to have alpha not equal to 0. Because alpha I is positive, right? So it's guaranteed they have to be larger than 0. Of course, bounded by C. Okay, so this is it. I actually tried to introduce this, give you an intuitive way to see that. So those points are very correctly predicted. Their alpha I will be 0. Those points on the boundary in the hard case, their alpha will be not 0, will be positive. So this is the soft case.
actually hard case. This showing a hard case. It's a one hard SVM case, and then you can derive it just exactly what I was trying to do in the previous page. This, yeah, it's the same. I tried to derive it. So to summarize, the majority of the data points alpha I will be 0. And those points in the hard case whose alpha I are not 0 are called support vectors. So this just, then let's go back to see what is W and alpha's relationships. Because W equals to alpha I, xi, yi, the majority of alpha equal to 0, which means what? For those points who are predicted very nicely, they really don't influence the W at all. No influence for those points very nicely predicted. Only those points on the margin contributes the definition of W. So again, so this related to the testing, which we already did. So this formulation is the dot product with all the training samples, because W equals to the summation of all the training samples. But in fact, during testing, what you really need is only those points have alpha I not equal to 0. Okay, now let's see the support vector for the soft SVM case. It's a little bit complicated than the hard case. So those points on the two sides, on the margin, so I think it's actually on the two boundary, their alpha are bounded by 0 and c. And those are in the inside the margin, their alpha is capped with c. And how to derive it, I have some proofs, derivations in the extra slide. Feel free to check it out. Okay, so now the next question is the C control of the balance of the area versus the margin size related to the number of support vectors? But actually, no. So sometimes people feel like maybe the larger the C, the more support vector, or the smaller the C, the less number of support vector. Actually, no. So there's no clear analytical relationship with the C and the number of support vectors. So keep that in mind. And feel free to read this, and this is totally extra. Okay, so I want to actually, because we have about 12 minutes left, so there's something extra, very extra, like from the kernel, we did not finish last time. So I still want to quickly talk about it. Okay, so kernel, we talk about kernel, right? It's the definition of phi x transposition phi z. And why do SVM work? So now you understand the dual formulation, and also the properties of the dual formulation is to make the alpha mostly 0. And now you also learned about kernel representation, which is an implicit way to project data points from X space to phi X space, right? So why do SVM work? You know, X to phi X in the RBF case, it goes to infinite size. Now, like, it's very easy to think about the bias and variance trade-off, right? You have such a flexible model. You're using this infinite size of space to represent my point. Why not overfitting? The reason is, even though it's a huge feature space, the number of parameters remain the same. So let's come back to what I just covered. How many parameters in the dual form of SVM? I just covered. We tried to do the comparison. N. So it's fixed with actually ON, right? It's not about feature fee size at all. It's about alpha, the number of alpha here. So no matter how flexible that feature space really are, I'm having a fixed number of parameters. The other is we only care about support vectors. Only the support vectors control my W, and there are normally a very small group of vectors. And the maximize of the margin, it's a very good generalization, right? Which we try to have some flavor in the ridge regression case. So why do you want to regularize, right? What do regularization mean? If you still remember, the L2 type of regularization is penalize the large weights, right? You're trying to make the weights kind of similar, not too extreme. So it leads to this, you can actually prove it, this type of margin definition leads to the reduce of the overfitting. So the combination is control the parameter size, at the same time control the margin is a regularization. It's two different type of control. But it's extremely flexible at the same time. So just let's review kernel matrix. It's really just for all the possible pairwise training data, you're going to calculate KXI, and that KXI is phi xi transposition phi xj. But you don't need to have explicit form. You only need to just know how to calculate this directly. In the original form, this is the X transposition X for training, and this is the kernel form. And there's also theorem if if you project it to a really large space, it can in generally very nicely separated or mostly separated by allowing just smaller areas in the margin. So this is the test formulation when using the kernel, using the original feature versus using the kernel feature. You can tell, almost nothing is changed unless, as long as you have this matrix already available. So this is the RBF proofs, and please, if you're interested, please feel free to watch the video from Caltech, and that specific session gave a really good explanation about RBF and also its projected space and also the properties of the kernel and why. So they're pretty nice summarized. And also we summarize the computational cost is OPN quadratic because you need to calculate all the pairwise, so there are totally n samples. So get that kernel matrix, it's n quadratic operation. For each of the KXIJ, it needs OP. So this is like OP cost. And then you need to do n quadratic such pairwise computation among all the samples, pairwise samples. This sample versus all the other samples. All right, question about this? So again, OPN quadratic. Okay. So a little bit extra is, so like I roughly said, as long as you have a similarity function, you can be thought of as a similarity measure between the input objects. But it's not every possible similarity measure will work. And there's some certain property you have to guarantee for that kernel matrix. It's the positive semi-definite property, which we actually had some explanation in our regression lesson. So feel free to read why this is the case. It's actually very easy to prove it. Yeah, why that needs to be positive, semi-definite. Okay, so now next is the most tricky part of using SVM is what kernel function to use. And the kernel function is important because it summarizes almost everything about the data. I don't even use the X at all. I only use K. I only use that matrix, kernel pairwise similarity relationships. So, but this actually is also good, right? Because for a lot of domains, it's very difficult, like I said, to come out the numerical representation of X, but it's very easy to come out a similarity function among the objects, like string to string, graph to graph, string to string, graph to graph, or maybe some sets to sets. So all those discrete type of data structures can design some similarity functions. Then you can use the whole paradigm of supervised vector machine to perform very nicely theoretically guaranteed classification. So kernel trick is really helped non-traditional data to be able to fit into the formulation to perform nicely formulated classification, theoretically guaranteed. It's a good balance of bias and variance trade-off, right? If you remember, it's fixed size of parameters, regularization through the margin or through the L2 norm. So it's pretty difficult, like if you think about k-nearest neighbor and all those, and it's not that easy to add all those other terms to regularize. However, SVM is a good combination of those framework from STAT and plus this flexibility of designing the kernel functions to make them work on non-traditional data. All right, so you might go confused about this definition called kernel. And if you already learned in some other classes something called kernel regression, the kernel here is different from the definition of kernel in those kernel regressions. You can think about the supposed vector machine's kernel, it's the Mercer kernels, and those kernel regression-based kernels are called smoothing kernels. So this is totally extra. Feel free to check it out. But they are actually two different concepts. All right, 2 minutes left, and then that's the last part of SVM is I talk about practical guide about pre-processing. There are 4 different kinds about feature processing. And then the last important part is model selection. So how do you select C? How do you select kernels? Again, like we always do. So this already showed, you can make the choices with RBF or polynomial kernels. There are also a lot of kernels, other type of kernels provided by libSVM. But you have to tune the parameter of RBFR or maybe gamma. And you also need to control this parameter. There are 2 parameters here, the D. So there are C, there are also kernel-specific hyperparameters. How do you select? You do grid search. So you try all the possible values of those hyperparameters, and inside cross-validation on train to pick the best combination of hyperparameters reflected on the cross-validation. But you don't do tests in your current formulation because the test, there's no label in the test. So we are the person who give you the test performance. So you have the test data, but you don't touch the test data in the cross-validation and use those only to apply your best learned hyperparameters and then retrain the whole model using the best hyperparameter configurations for this full model and apply on the test data we share with our labels and then submit that predicted label files. And this is more like a simulation of where imitate how truly like a Kaggle competition or those. So you do cross-validation to pick the best hyperparameter, and there's a organizers to judge who's the best. And this is the more details, provided from a scikit-learn that Practified, and I think it's a pretty good guide. And in general, RBIF is a very nice, solid kernel. All right, so this is more provided by the scikit-learn project guide. Just feel free to check it, follow their pipelines, and this is everything we want to cover about SVM. And just last chance, questions, concerns about homework, because I know there are two things